The rear wing is becoming obsolete, and the engineers who figured out why are the same ones building the fastest road cars ever made. For the last 50 years, the rear wing was the answer to one question: how do you keep a 1,000-horsepower car on the ground at 250 miles per hour? You bolt a wing to it, you angle it, you let it bite the air and push the car down. Simple, works, everyone does it. Except it doesn't work cleanly. Every wing that generates downforce also generates drag. That's not an opinion, that's physics. The same force keeping your tires planted is bleeding off your top speed. You're always trading one for the other. The Bugatti Veyron ran a massive rear wing and hit a 253-mile-per-hour wall for years. Push past it, and the wing trying to save you starts costing you. And wings are reactive. They only work when air is moving over them fast enough. At low speeds, city driving, tight corners, anything under 80 miles per hour, the wing is dead weight, literally. You're hauling around a carbon fiber spoiler that does nothing until you're already fast enough that you probably didn't need more grip anyway. So engineers have known for decades that the wing is a compromise, a necessary one, until it wasn't. Ground effect is not a new idea. F1 used it in the late 70s and immediately banned it because the cars became so planted that when the suction broke, and it broke suddenly with no warning, drivers had zero chance of recovery. Lauda called it terrifying. Other drivers didn't live to say anything. The concept is simple. Instead of pushing the car down from above, you pull it down from below. You shape the underfloor of the car so that air accelerating under the body creates a low pressure zone. Low pressure underneath, normal pressure on top, and the car gets sucked toward the road. The harder you go, the stronger the suction. No wing required. The downforce numbers are staggering. A properly designed diffuser and underfloor can generate more downforce than any rear wing, and it does it with almost no drag penalty because the air is being managed under the car, not fought from above. F1 figured this out 50 years ago. Road car engineers just spent the last 10 years actually solving the safety problem that got it banned.
Here's what makes this more interesting than just an engineering footnote. The cars getting ground effect right aren't experimental prototypes. They're being delivered to customers. You can buy one. The Bugatti Tourbillon, the Gordon Murray T50, the Ferrari SF90 XX, the Koenigsegg Jesko Absolut. All of them are shifting serious development resources away from traditional aerodynamic packages and toward active underfloor management. And what they're finding is that the performance gap isn't marginal, it's massive. A fixed rear wing in high downforce mode might generate 400 pounds of rear downforce at 150 miles per hour. An optimized active underfloor at the same speed can hit 800, 900, even over 1,000 pounds, and keep climbing proportionally as speed increases. Because the faster the air moves under the car, the stronger the effect gets. That relationship is non-linear. The faster you go, the more it compounds. Wings plateau, ground effect doesn't. And then there's the drag number. A hypercar running a high-angle rear wing at top speed can lose 20 to 30 miles of potential just from aerodynamic resistance. The Venom F5 Evolution ran minimal wings specifically because Hennessey knew that at 300 miles per hour, drag is the enemy, and the numbers don't forgive compromise. Ground effect lets you generate enormous downforce and keep the body slippery. You're not choosing between grip and speed anymore. That used to be the fundamental constraint of hypercar design. Now it isn't.
Gordon Murray built the McLaren F1. He knows exactly what a rear wing cost you. When he designed the T50, he didn't use one. Instead, the T50 runs a 400mm fan mounted at the rear, not a wing, that actively evacuates air from under the car on demand. At full suction, it generates over 1,500 pounds of downforce. The entire body is shaped as a ground effect device. Murray spent more development time on the underfloor than on any other single component. The result is a car that weighs 2,160 pounds and hits 60 in 2.9 seconds from a naturally aspirated V12 making 654 horsepower. By hypercar math, those numbers are modest. By physics math, they're extraordinary because the car is generating grip without the aero drag that would normally accompany this much downforce. It handles because of how it manages air under the body, not because a wing is forcing it down. Murray has said the fan car concept is 30 years ahead of anything else on the road. Overstated? Maybe, but the underlying point is real. The car that defined the 90s hypercar era was basically aerodynamically primitive compared to what he built in 2022.
The reason this took so long to reach road cars isn't that engineers didn't know about it. They knew. The problem was control. In F1, ground effect works at race speeds on smooth circuits. The pressure under the car is consistent because the road surface is consistent and the speed is consistent. Ride height is locked down. The whole system is optimized for one thing. On public roads or even a racetrack with surface variation, ground effect is sensitive. Change the ride height by 10 millimeters and the downforce can drop by 30%. Hit a bump and the floor loses contact geometry and the suction partially collapses. Early active suspension systems weren't fast enough to maintain the underfloor gap. Control systems weren't sophisticated enough. The computational overhead was too high for road car development budgets. What changed is everything changed at once. Active suspension with millisecond response times is now production viable. The Pagani Huayra was using it in 2012. Modern systems are 3 generations beyond that. Computational fluid dynamics let engineers model underfloor behavior at a granularity that wasn't possible 15 years ago. Carbon fiber floor construction tolerances got tight enough to actually hold the geometries the simulations require. The engineering caught up to the physics. That's the only reason this is happening now and not in 2005.
The Bugatti Tourbillon's Aero package is worth explaining in detail because it shows where this is going. Bugatti engineers designed the Tourbillon with an active underbody system that adjusts in real time. The floor geometry changes with speed, steering input, and lateral load. At high speed, the diffuser opens aggressively to maximize suction. Under braking, the system redistributes balance front to rear to stabilize the car. In cornering, the inside and outside pressure distributions are actively managed. The rear wing is still there, but it's doing less work than on any previous Bugatti. It's handling edge cases. The primary downforce is coming from below. Bugatti calls this a hybrid aero philosophy, but what they really mean is that the wing is the backup and the underfloor is the main event. Compare that to the Chiron Supersport. Same DNA, totally different approach. Massive rear wing, massive drag, top speed of 304 miles per hour, which required an incredibly powerful drivetrain just to overcome what the wing costs you in resistance. The Tourbillon will likely hit comparable or higher speeds from a powertrain that isn't working as hard to get there because it's not fighting its own aerodynamics to do it. That's the clearest way to see how much a wing costs you. 2 Bugattis, one with a wing doing the heavy lifting, one without. The one without wins on efficiency.
So what does the next generation of hypercars actually look like? Lighter, cleaner, lower. The visual language of the hypercar is already changing, and ground effect is a big reason why. Cars don't need the towering rear wing stacks anymore. The Jesko Absolut's top speed configuration runs minimal wing. The Ferrari SF90 XX blends traditional aero elements with serious underfloor work. McLaren's most recent track-focused cars have consistently moved development resources toward the floor. The performance ceiling is rising too. Once you break the dependency on the wing drag compromise, the question becomes, how much downforce can the underfloor actually generate? Early numbers suggest the limit hasn't been found yet. Active systems running at race car ride heights on carbon floors with real-time computational management can theoretically generate downforce figures that passive wings could never touch. And the speed records are going to move. The 300-mile-per-hour barrier was crossed by the Venom F5 Evolution in 2024. The next benchmark is unclear, but the cars chasing it are all moving toward ground effect solutions. Koenigsegg is on record saying the Jesko Absolut's theoretical top speed is 330 miles per hour. Hennessey has talked about taking the F5 further. Both of those programs are aerodynamically constrained only by what the underfloor can do, not by what a wing can generate. The hypercar that holds the production top speed record in 5 years almost certainly won't have a traditional rear wing. It'll have an active floor, a diffuser optimized by simulations that ran on hardware that didn't exist 10 years ago, and a drag coefficient that would have seemed impossible when the Veyron was first designed. The wing isn't dead yet, but the engineers who are building the fastest cars in the world know it's not the future.
And the proof is already here. In 2025, the Yangwang U9 Xtreme hit 308 miles per hour, the fastest production car ever built. Engineers removed the rear wing entirely to do it. Nearly 3,000 horsepower on tap, and the wing was still the limiting factor. Without it, the record fell. Then, at the 2026 Beijing Auto Show, Xiaomi unveiled the Vision GT. No traditional wing, body shaped to channel air, aerodynamic structures integrated directly into the chassis, 1.2 tons of downforce, drag coefficient of 0.29. A smartphone company looked at the rear wing and decided it was the wrong answer, and the numbers proved them right. From a production record in Germany to a concept stage in Beijing, every serious engineer is landing in the same place. The wing is not the future.
The wing dominated hypercar design for 50 years. Now the fastest engineers on the planet are walking away from it. One record run, one concept stage at a time. So tell me, do you think the rear wing is finished, or is it still the answer? Comment below. And if you want a full deep dive on the Xiaomi Vision GT and what it means for the future of hypercar design, that video is next.